All right, hello and welcome to LCU14-313 Advanced Toolchain Usage. So this is actually a two-part discussion. We will do the normal presentation here for nearly 50 minutes, and we'll take a break and we'll do part two. It's the same slide deck for both presentations. You can find the slide deck on Zarista. For the online participants, you can use an Etherpad to collaborate with us. I'll be looking for questions in the little chat window down in the corner. I will also be taking notes there. There is a lag between the presentation and what we're presenting and what you're seeing online if you're participating online. So please use the Etherpad. For the benefit of the recording and for our video archive, if you have a question or comment, raise your hand. Renata will walk around with a mic, get you a mic so you can ask your question. Today's presenters are Maxim Kuvyrkov. He is the Lenaro Toolchain Tech Lead. We have Michael Collison, who is an assignee from ARM working with us, and Will Newton, who is our System Libraries Toolchain Team Lead. All right, so I think Michael's starting it.
Thank you. So we've got a part one and a part two. So I'm going to go ahead and I'm going to first cover GCC optimization levels. I'm going to assume that most of you are pretty comfortable, and I'm just going to go through this very quickly. If you have any questions about any optimization levels, please stop me. Otherwise, I'll assume that you're pretty familiar with this.
Can you just quickly go over kind of what the point of the whole presentation is?
Sure. Yeah, I mean the point of this presentation is we're assuming that you're comfortable with GCC, that you're power users, and we'd like to show you a few interesting things that you can do with the compiler. Like we're going to talk a little bit about LTO. We're going to talk about feedback-corrected optimizations, inline. So since these guys are a lot smarter than me, they gave me the more basic things like the optimization switches. So, but we will talk about some of the more advanced things here. All right. So I'm going to start off with the optimization levels. So if you use GCC any length of time, you're probably familiar with most of these. So I'm going to go ahead and just touch on what happens at a very high level at each optimization level. So -0 is equivalent to no optimization. It's also equivalent to what would happen if you didn't specify any -O option on the command line. And this is actually the default if you don't specify anything. -01, very basic optimizations. Maybe if you're going through an edit, debug, compile cycle and you want to put -G, you might want to enable this. And in most cases, you wouldn't get too many surprises if you were single-stepping through the debugger. Okay?
Actually, what about OG?
Hey, I have that.
Oh.
Yeah, I talk about -OG.
No, when you said you turn it on for debugging, that's...
Yeah. I'll talk about it. Don't make me look bad.
Okay.
All right. O2, for most people, for me, once I've debugged, I typically will use -O2. Turns on more aggressive optimizations. Just as a little bit of history, when optimizations were added to compilers, initially you would optimize, let's say, an expression tree. Then compilers went to optimizing within a basic block. Then you went to optimizing within a function, and then you started optimizing within a file. -O2 for the most part you can kind of think of within a function and a little bit within a file depending on what optimizations you turn on. Okay. No questions so far? Okay. -O3, if you don't care about code size, you might want to go ahead and do -O3. It could potentially inline any function, so you could get huge code explosions. Sometimes it makes things better, sometimes it makes things worse. You can do function cloning. This one is pretty interesting where the compiler could make multiple copies of a function and potentially inline the function. If, let's say, you passed a constant, let's say you're calling one function with constant 5, the same function with constant 10, the compiler could actually clone the functions and optimize them with both of those constants. Okay. -OS. I actually come from an embedded background, very low-end mobile, where you really care about code size, where there's no kernel. You might use -OS if you cared about that. I know most of you are probably more A profile for ARM, so you may not care about this, but if you did, -OS would be something that would be interesting.
So yeah, I have a question about -03.
Yeah.
So is it possible for, usually -03 means that code will go faster. Is it possible for code go slower at -03, and in what cases or on what kind of systems?
Yeah, I mean, certainly code could go slower because of a code explosion. You may begin to have problems with register pressure, so you may end up spilling a lot of things to memory. In theory, it could make your code slower, certainly at 03. Yeah.
Or, for example, if you have a small embedded target and you have small caches, and suddenly your loop doesn't fit inside your cache.
Yeah. Absolutely. Was there another question?
I'd just like to point out a few differences.
Okay.
On LLVM. It's mostly the same. Is that the vectorizer, SIMD vectorizer, is enabled on O2 and OS, because we have the OZ.
Okay.
The OZ is the same as your OS, but our OS is like OZ with vectorization and some other code reducing optimizations.
Okay.
So it's just, and it's.
I could actually tell the history on that one. It's an Apple thing. At Apple, they turned on OS, and then it was found out that they didn't have. So it's actually a PowerPC related thing. They basically, there's these, just like under ARM, there's load multiple.
Mm-hmm.
So basically, they found that wasn't turned on in OS, so they were okay with that. But then in later versions, it was turned on, and people started complaining. Internally in Apple, they started complaining, and so that's where the OZ comes from.
All right. Okay. Excuse me? Oh, yeah, 03.
So OFast, do you have a slide for OFast?
No, I don't have a slide.
Okay, so OFast is basically 03 plus fast math and unsafe math optimization, loop optimizations. So it actually depends. It actually says loop indexes never overflow. For fast math, it turns basically, it can reorder things, it can remove, it assumes no nans, no infinities for floating points and a few other things.
I would say personally, I would stay away from that unless you can really prove that it improves your application that much. I mean, in general, as probably most of us know, you can get more improvements by improving the algorithm than enabling some unsafe optimizations that may work in this release. It may not work in the next release for your application. So, right? All right. Touched OS-OG. As pointed out earlier, this is the newest level. I'm not sure what version this was actually released in, but this is the optimization level that you would prefer to use if you're going through an edit debug compile. So like I said, -O, but this is really the preferred one with -OG. You do still need to use -G on the command line with this one. So again, you wouldn't get as many surprises when you're stepping and single stepping, things like that.
Yeah, but compiler code would still look much better.
Yes.
Than just -O0 with -OG.
Right.
With -G.
It was added in 4.8.
4.8, okay. All right. Just some quick recommendations. I kind of already touched on this. -OG and -G if you're kind of going through edit, debug, compile cycle. -O2, code size and execution are kind of balanced. -O3 if execution speed is the primary. -OS when code size is primary. I'm going to touch a little, have a later slide on LTO where I'll talk a little bit more about LTO where that could actually help significantly depending on your application. Questions on this part?
Yeah. Any questions on optimization levels?
How safe is L3 in terms of
edit-compile-debug, and very.
Yeah, very safe. In my experience, it's very safe.
So by default, most of the GC test suite is compiled, all the test cases in GC test suite is compiled with, I think, all this, -02, -03, -OS. I don't think it's compiled with -OG yet.
Yes, it is.
Okay.
Yes, it is.
Yes,
So,
I added that.
And also LTO, I believe, as well.
yeah, so all these compiler options are fully supported.
So I believe in LLVM that FastMath allows you to use neon in situations where it's faster and you don't need perfect accuracy from your floats. Is that true for GCC as well?
Yes.
Yeah, okay, so it may be worth it in cases like that.
D-norms.
Yeah, but that's unsafe math optimization.
Yeah, well, basically D-norms. So basically, Neon on ARch32 D-norms are not supported, and so D-norms get flushed to 0. So and that's the reason why it's enabled only for FastMath now. It wasn't at one point. It actually changed more recently. But for ARch64, D-norms are handled, so it's always on. On ARch64, D-norms are handled for SIMD. So they're handled correctly in all the floating point. The floating point and the SIMD are overlap.
So there is a question here on the Etherpad. Is there any list of optimizations performed for -OS?
A list of optimizations. Normal copy propagation, inlining is not performed.
Actually, inlining is.
Yeah, yeah, basically.
OG, it's not unless you have always inline.
Right.
So OS has inlining.
It's O2. Oh, excuse me. Sorry. It's O2 with the exception of what I listed here.
Plus a little bit more.
OS. Okay.
There's a little bit more.
Okay.
For an example, if the function is called only once, it inlines it. It's turned on. Also, there's like one other. It's the inlining heuristics is turned way low, and also it inlines even functions that are not declared static. So with the inlining heuristics turned way low, it tries to figure out that, is it better to inline it? In some cases, this actually is better to inline it for OS.
Okay, sounds good. Moving on to the next topic. And what if a software developer is really experienced and he or she wrote an application and then got hold of GC manual and tried every single option, of which there are, I think, close to 100 from GC. And there are big software projects that do this when they need to deliver their system, which would run several percent faster because someone promised it. So what they do is that they take several compilers, they try every single option from the compiler, disable optimization, disable some optimizations, enable others, and they figure out what was the best particular set of optimization for their source code. And that works for a year until several compiler versions later, someone in the from the GC community or LLVM community rebalanced the options, so now, or added some new optimizations. So now, for some reason, all those hand tuning and figuring out what the best set of flags are for a particular application is no longer valid. Our recommendation is to only use one of the standard optimization levels. because this is what compiler developers always test for. This is what they make sure compiler generates good code for. And if you add a new compiler flag which disables scheduling or disables or increases loop unrolling, that might get you some short-term benefit, but you will need to redo this tuning with pretty much every major version of the compiler. So GCC for 4 tuning will be not valid, most likely for GCC for 5 tuning. And with compiler versions releasing each year, you will have to spend each day, several days each year, just to maintain your sets of options.
And if they want to introduce or remove a pass from an O level, they will run several tests on many different architectures to make sure that it's not hurting anything. So it's more proven than your own stuff.
Okay. So try not to do that. It's not a good idea. And by the way, it's also quite likely to make your code buggy, because compilers have bugs. We test them, we fix bugs, but we don't test every single combination of options out there. On the other hand, there are some flags that it's okay to use even if they are not the default. So there are feature flags, compatibility flags, and optimization flags. For feature flags, if you move to a new language standard, then you obviously need to enable it. If by default the GCC compiles for C90 with the GNU extensions, and LLVM compiles for C99 for the C compiler. I don't really remember.
GNU actually, GNU 90.
Yeah.
And LLVM is GNU 99.
So GC compiles for GNU 90 and LLVM for GNU 99. There is a common option that makes code go slightly faster. So you will see it in benchmarks of no-common, which affects just a little bit the C language standard correctness of your program, but for most applications it is safe to use. And then, of course, the selection of your particular target. If you are using a native compiler and you're compiling your application natively, this probably should not be a concern for you. If you are using a cross compiler, then you should definitely use correct target options. Compatibility flags. The most two common ones is no strict aliasing, which works around a particular form of programming that was popular in the 80s and 90s in C language, which is then became non-standard with, I think, C90 or C89.
There's part of C89, but actually there's some mention of it in K-nor-C, just nobody followed it.
Yeah. And if you are casting pointers from one type to the other, early compilers in the 80s and 90s allowed that and generated correct code. Now that compilers try to use every loophole in the standard and treat any undefined behavior towards their own preference, in other words, to make code go faster, they are very likely to break pointer casting because alias analysis got much better in recent compilers. And the other one, if f signed char, it's until I joined Linaro, I did not know that char is not signed in standard. So it can be signed, it can be unsigned, and this is an implementation-defined feature. So for example, on most of the targets out there, char is signed by default, but on ARX64, it is unsigned
And
by default.
both ARMs and also PowerPC.
Both ARMs.
And also PowerPC.
And PowerPC.
So there is a compatibility flag there's two more that you missed. frapv or no strict overflow.
Yes, those are two. I think of them as less common, so these are the two.
They've become more common in the last 4 years. They were definitely less common about 10 years ago, but since now GCC is also, and I think LVM to some extent, I don't know what the flags are for LVM, but in the recent ones, there's been quite a few of problems that have showed up due to signed overflow as being undefined. Now, and then again, the undefined sanitizers actually can detect that too.
Nice. Thank you. And this slide is enumeration of various defaults from compiler toolchain vendors, what will happen and how your code will be compiled if you do not select any target or specific options.
Recently, I have seen like in spec benchmarks, some of benchmarks failed, and the compatibility fact what GCC suggested is to use no aggressive loop optimization. You want to comment on that, Andrew?
Which one?
No aggressive loop optimization. So some of the benchmarks failed, and we started using it.
Interestingly, this option is pretty much specific. Was added specifically to address Spec 2006, some of the benchmarks in Spec 2006. No aggressive loop optimization.
That's also signed to overflow. It's just using it in loops instead of not. Oh no, I take that back. It is due to signed to overflow. It's also due to writing past a buffer. So that's something that they looked at and they're like, oh. So GCC started using the array sizes as the bound of the loop, and well, there's bugs in some people's codes, and people, obviously the undefined sanitizer might detect it, or the address sanitizer would have detected it also.
I run into it when I was running spec on LLVM, and I find it hard to believe that nobody ever fixed this in the source.
I'm not.
So there is a question coming up on Etherpad. Is the recommendation, if the recommendation is to use standard optimization options, O2 or 3 OS, why options such as -F is still supported? They are, I don't want to say just for compiler developers, but my opinion is yes, they are to make compiler developers' life easier, and when a person reports a bug in the compiler or thinks that he or she found the bug in the compiler, these options are very handy to reduce it down to a single optimization. Especially this is helpful when a person is working on a proprietary source base, so they cannot share the test case on which compiler fails. So instead they can show some logs from compilation and with help of compiler developers reduce the problem down to an optimization, a single optimization.
This is also very useful for testing.
This is also, yes, very useful for testing. And if you think about it, whenever a new optimization is added to the compiler, compiler developers are always not trusting it by default. So they want an ability to quickly test whether the new bug that they're seeing is due to this new optimization that was added just last week. And having a flag that turns it off is convenient. And in the end, what -O2, -O3, and all other -O options do is that they correspond to a specific set of -F flags. They do nothing more than enable a bunch of -F flags.
In the right order.
In the right order.
Except
There is an except, but that's a nitty-gritty detail.
There actually is a big exception, at least for GCC. I don't know about LLVM per se, but you can't go from OG to O1, or you can't go from O0 to O1, or even. What do I mean by can't go? I mean you can't. There's no flags to change it except. So OS actually enables something separate internally to say optimize for size, and the same thing is true for OG. Actually, OG has a different optimization pipeline.
Yeah, I think it's similar. I mean, you cannot say O0 and then F whatever and then be exactly the same as O1.
Exactly, or even going from O2, there's no flag to go from O2 and add a couple of extra flags to get OS.
Okay, so for the defaults, the slide was up there for some time, so if anyone has any questions, tell me, otherwise we are going to skip the slide.
Okay, that was actually on the -F thing. Presumably you could also use that to switch off a buggy optimization temporarily. Yes. Would you consider that a safe thing to do, given that you've just been telling us not to throw those switches?
As a workaround for a bug, yes.
As a temporary thing, yeah.
Yes. Very temporary.
Yeah. But then there's some danger that by having switched that off, you might trigger some untested set of optimizations.
Alex?
Yeah. My question is, what's the difference between the Linux and the Ubuntu? I only find the last parameter is Cortex A9 or Cortex A8. I suppose there are some instruction different. So, but this is kind of change can cause some performance or some execution binary size or some even power change.
So all of the defaults is pretty much a history, how it came up to be. In case of Linaro versus Ubuntu, why one tunes for Cortex A9 versus the other for Cortex A8, I'm guessing is what was the dominant hardware out there at the point when the toolchain was first released. And that's it. And we are going to touch more on mtune and mcpu options later, so I will return to this point on one of the next slides.
Okay. Okay.
Anything else on the defaults? Okay, moving on. So when doing cross-compiling or trying to get the best performance for a native compilation, it's always a good idea to use just to give to the compiler the exact machine that code will be running on. Two main options for ARM are -mcpu and -mfpu options. For most of the current hardware, I would expect that -mcpu Cortex A15 with latest Neon unit would be the options that you see up there. -mcpu is a newer option compared to -mark and mtune. Initially, GC only had mark and mtune options, and then they were unified to be the one. The difference between these three options is that -mark selects instruction set and capabilities of the hardware, and -mtune selects the internal workings of the chip, like its pipeline, its cache sizes, and other things that affect performance but do not affect the correctness of the program. So with -mark, you can specify -mark ARM v5 and mtune Cortex A15. It will generate only v5 code, and that code will run on any ARM v5 part, but it will also try to be quite performant on Cortex A15 machines, because the code will be scheduled for instruction scheduling will be performed for A15 instead of older A5 chips. So the other important point, which is not often discussed, is when you do cross-compilation, all your toolchain and all your toolchain libraries are on the host machine. And whenever you do dynamic linking, you need to make sure that your target, where you copy your application, also has the matching set of libraries from the compiler that the application was linked against. Generally, it is a very bad idea to use a new compiler like GC49 and not copy GC library and keep the libraries from your system and try to run, for example, if you have a native compiler on the target system GC46 and you have compiled your application with GC49, your application might run against GC46 libraries on the target, but it also is likely to crash. Especially so if you are trying to use sanitizers or C++ library or any of the non-C standard features in the compiler in your application. It is possible to support more than one set of target libraries in a single compiler toolchain. Some vendors do that. At Linaro, we prefer to always have a single set of target libraries for a toolchain package. So in our toolchain package, you will only find a single multilib. If you want to have, and from the previous slide, you saw that it will be an ARMv5, because by default we compile for ARMv5, or we don't. It's ARMv7. Yes, so by default we compile for ARMv7, and you will find, if you want to run your application on ARMv5 hardware, you will need to rebuild the toolchain or get one from other source. Instead of trying to support both hard float and soft float sets of libraries in one toolchain, we rather provide two different toolchains, one for soft float and one for hard float. And this is our strategy for handling different APIs and different sets of API-related options. Any questions on target flags, multilibs?
There's a question here. So you read the previous question. It says the previous question says that the points discussed in the session are very good. Will they be put in the online docs? So I will put these in to Zarista, but the follow-on question is, can the session summary be put in GCC documentation? So Andrew has a comment on that.
Some of the O2 stuff and OS and OG is already there. It's just we're summarizing and providing an extra summary on top of the GCC summary, documentation summary, for, just to give you a general overview. There are a few things that, reorg of documentation is always nice and useful. So if anybody's volunteering to do that, that's one thing that would be nice. We're not all document writers. In terms of the compatibility, if it's a compatibility flag versus a other flag, that's kind of in there, but not exactly, and should be, but we just don't have the resources, to do, well, nobody's volunteered to do it yet.
Okay. We have a question from Alex.
Yeah. Still back to the CPU typo. If you use the A15, you compile your binary with A15, but you use it on the A9. So I suppose there are some new instructions in the A15. So if you do that, if it is possible to cross into some undefined instruction error.
So if you compile for Cortex A15 using the -mcpu option,
yeah,
then yes, it's possible that. So in your example, both parts are ARMv7, as Will points out. So there are no new instructions in Cortex A15 compared to Cortex A9.
No new instructions.
No new instructions because they share the same architecture, ARMv7A.
Okay.
So for Cortex A15. So for Cortex A15 and Cortex A9, I think there is division instruction, the integer division, and there is no integer division in Cortex A8 and A9.
When doing neon intrinsics or inline, you need to do the -mfpu neon. That also controls the code generation of the C code, and if you're doing runtime dispatching, you'd like to tell it to generate. I'd like it to generate C code that isn't neon, but still allow the assembler to do neon inline or intrinsics, which you can do with Intel x86.
Yes, so the answer to this is
Would you repeat the question?
The question was whether it's possible to not make compiler use any neon instructions when generating when compiling from C code to assembly, but still allow for assembler to accept neon instructions. So, like there are some inline assembly in the code that generates neon only after detecting that neon unit is actually present, something like that. The answer to that is to use -WA option, which will, so there are two quite useful options. -WA, which will pass any given option to assembler directly, so compiler will just not look at it, it will proxy it to assembler, and corresponding linker option is -WL. So you can put them on the compilation line. A compiler driver will pass it directly to the linker or assembler. Compiler itself will not, will disregard that option.
So there is another option, but I don't know if it's supported for ARH32 or even ARH64 yet. There is a way to use attributes on the function that you're trying to compile to say this function has neon in it, and it will allow it. But I don't know. I don't think they're supported. They're not supported yet. That's something that probably should be on the roadmap somewhere by somebody. What? No, unrelated .funcs. So on x86, you actually have target options that you can add to specific functions. And also, well, they also added a feature which you can say compile this function in multiple ways and select based on the architecture. But that's not supported yet for ARM32 or even ARM64.
something like that. Yes.
There's another question.
So, last question we will take on this topic is there any specific reason for Linaro to release different toolchains for soft flow? Can you explain the reason to use this strategy? Yes, there is a reason. The reason is to, I think, Rob, do you want to take this question or should I answer? So why we are using different toolchain packages for soft float and hard float ARM?
Well, there's still some old ARM hardware out there without hardware floating point.
So the main reason is that there is not a standardized format for multilib. So Ubuntu has their own version. I assume Red Hat products have their version. The way the compiler defines multilib is it defines it as an internal structure, but each distro wants to ship their own methodology. It also increases, so there's that confusion. We would have to maintain our own. There's also, it increases the maintenance cost, and it's much less confusing if we have a soft float targeted toolchain entirely. I do realize that does increase the complexity, or it increases the dependencies that some of the users have if they have to have both of these installed on their target. But from the maintenance perspective and support perspective, it's easier for us. So,
yeah, because I have like 6 different patches that do multi-libs, and they're all different.
Moving on to feedback directed optimizations.
We're out of time, so let's take a break.
Okay.
And then we'll just pick up.
So we will continue with feedback directed optimizations after the break.
On the next session.
Yes, so
it's a new session.
It's a new session, still the same room, same people.
Yep, so the online viewers, I believe you're going to have to go to the stream for the next session to pick up this stream. I will also move to the next Etherpad for the next session. So we'll be back here in 10 to 15 minutes.